work on weak acids and bases. Remember, if it's a weak acid or base, it doesn't completely dissociate. It only partially dissociates, and so that means we have an equilibrium reaction. For example, NH3 is a weak base. So when it reacts with water, some of it will take a hydrogen away from water and become ammonium ion and produce OH minus in water. But actually most of it will stay as NH3, ammonia. So this is a reaction that happens in both directions, which means we have an equilibrium, which means we can solve for K. Remember, your K, you're not going to use your liquid. So the K is going to be your NH4 plus times OH minus divided by your weak base. So really it is the dissociation, the two ions multiplied their concentration divided by the concentration of the weak acid or base. And we are going to need to use a Rice setup because we are talking about things in equilibrium. And when you put in a weak acid or base concentration, its initial concentration is not the same as the equilibrium concentration of either the OH or the H plus. So I know you love Rice tables, but luckily there is a shortcut, so you don't have to use the Rice tables. But if you don't memorize the shortcut equation, then you must derive it from the Rice table. So remember, Rice, R is reaction, I is initial concentration, C is change, and weak acids or bases, we're just going to have X, no 2X, no 3X, so it makes your math easier. E is still the equilibrium concentration. What you need to pay attention to is that when you're working with a Ka, the X that you're solving for solves for concentration of H plus because acids contribute H plus to solution. If you're working with a Kb, your X that you're solving for is going to be your OH minus, remember, because bases contribute OH minus to solution. So the shortcut is that K is equal to X squared over initial. And then the second shortcut is X is equal to the square root of K, oh my goodness, sorry, times initial. Well, we can do this because it's assumed that weak acids and bases dissociate so little that we can kind of neglect the fact that some of the initial concentration of the acid or base is going to be taken away from it. Technically, the initial concentration of the acid or base stays almost exactly the same. So we can figure out our percent dissociation. It is your X divided by initial times 100. So as long as percent dissociation is less than 5%, we can neglect the fact that some of the concentration of the initial weak acid or base is going to be used, and we can use the fact that K is going to be X squared over initial. So we're not subtracting really anything from this initial. All right, so let's do a problem. We want to calculate the pH and percent dissociation if we have a 1 molar solution of hypochlorous acid, that is a weak acid. Look, we're given a Ka. So that means that our X that we're solving for in this problem is the concentration of H plus because we're dealing with Ka. So we're going to first solve for our X. We're going to use this shortcut that K is equal to X squared over our initial. The initial must always be given to you, which it is. Right here, that's your initial. So we're going to say that K, which is 3.5 times 10 to the negative 8, is equal to X squared, which we're solving for, over initial, which is 0.1. And that can be be written in our other shortcut equation, x equals square root of k times initial. So, x equals square root of k times initial. Alright, so x is equal to the square root of 3.5 times 10 to the negative 8 times the initial, which is 0.1. Use the writing. The pen's not working. Alright, so when you plug that in, you get that your x is equal to 5.9 times 10 to the negative 5th. That is a molarity, and it's the molarity of what? Oh, H plus, because it's X. So, if I want pH, and I have concentration of H plus, woo, stop writing. Okay, where's it? Sorry. Anyways, so if we have the concentration of H plus, we can find our pH. pH is equal to the negative log of H plus, which is our 5.9 times 10 to the negative 5th. Trust me on that. All right, plug it into your calculator, and your pH that it spits out is 4.22. Sorry about the mess. Anyways, the last part is percent dissociation. It's just x over initial times 100. While x is 5.9 times 10 to the negative 5th, our initial is 0.1, so it's just math. I know it scares you. 10 to the negative 5th, again, sorry about the handwriting, times 100. When you plug that in, it's a very small number, which is good. We want our percent dissociation to be small. Our percent dissociation equals 0.059%. Alright, so practice that on your own.